Okay, we're recording and welcome to Thursday. So what I would like to do is start by going over the quiz. And again, invite Professor Baker to pause as needed. Um, Pause as needed if you want to add some comments, or you can discuss it later. But again, at the end of quiz one, we give you a few hints of what to look for on the video. And yes, we know it's old and certainly the technology is outdated, but I think the concepts are certainly valid. And so the revolutionary breakthrough described in the video that allows us to make the violins that sound like antique Stradivarius violins came from the observation that the wood was aged in water and therefore what happened. And I think the key demonstration here is when he puts the seasoned and unseasoned wood into the aquarium tank, and one sinks and the other floats. And so the wood that was aged in water, the bacteria eat out the cell membranes. And so basically you have, that's open, the water will go into that and it will sink. But also that greatly affects the sound properties and makes a very rigid, light structure, but then the sound can go through it. It's not blocked by the cell membranes. And apparently this makes a big difference. And, whether it was a genius or sort of accidental good luck on the part of Stradivarius, that was one of the key elements that seemed to make a big difference in the violins. So anyway, that was quite neat. And again, back when this video was made, to do the spectral decomposition, you needed about $20,000 worth of specialized equipment. But what's very nice is these days, any cell phone and a TE tuner, which I recommend, can do it real time for a transform spectral decomposition. And then you can we're going to be doing some of these things in lab later on. So I thought that was very interesting. The second point is, what is the point of the demonstration? The orchestra playing Symphony 6 of Tchaikovsky. And what they did, if you recall in the video, they put the first and second violins in the older format where they're on opposite sides of the stage. And then what happened is each one of those did not have the full melody. So for example, the first violins were playing dee doo dee doo dee doo, and the second violins were playing doo dee doo dee doo dee. But then what your brain does is it fuses because it's used to hearing notes that are close together. And even though no instrument is actually playing the melody, you clearly hear that melody coming through. You hear the top line, you hear the bottom line, and your brain fuses those together. And Tchaikovsky was aware of this and actually used it to his advantage in the symphony. So that was a beautiful demonstration. And finally, what is the difference about the new bells that were demonstrated in the video? And you notice the new bells had the thicker top. They didn't have the traditional bell shape. They're a little bit odd. They had the thicker top. And what that did was basically it shifted. The bells are not a fully harmonic instrument. The overtone series, we'll look at that later again when we use our cell phones to do the spectral decomposition. But what's neat about them is that the traditional bell shape typically has a minor third. And the new bells, that shifted that harmonic up to a major third, which for non-carillon players was more favorable. And when they did the comparisons with the traditional carillon players, they were used to the traditional bells with the minor third, but the musicians that were not used to that actually preferred the new bells with the major third. But that's quite complicated. In fact, we'll do some of the Chladni plates in lab and get to see why that's the case. So anyway, and again, 2 out of 3, and I will grade it. We don't need a novel, but if you get the key point, that's good enough. And hopefully everybody watched the video and got 100. And again, you're off to a fine start in this course. So the next thing I would like to do is take a look at a few things from the chapter, to get you up to speed at that. And again, we're not going to go heavy in the math and we lead you through it. So, this is about as much as you're going to do, but I do want to kind of take you through it a little bit. And we're going to start with some very simple example. So we're going to do units and conversions. And let me get my annotation out here so I can, let's see. Yeah, that's good. Yeah, okay. Yeah, so units and conversions, and then we'll start with this formula. And so this x equals vt, that means distance is velocity times time. And you sort of know that intuitively. So Austin is about 200 miles south of us in I-35. So if I get in my car and I drive 50 miles an hour, maybe I'm driving slower than you usually do, how long will it take me? Well, you sort of know intuitively. If I just say it's 200 miles, I drive 50 miles an hour, you can almost, without calculating, say, yeah, it'll take about 4 hours. Austin's about 4 hours. But let's work it out. So using this formula, the distance, okay, if I drive 50 miles an hour, and if I do that for 4 hours, okay, and now I'm putting in the units because that's going to guide us. Velocity is in miles per hour, and time is in hours. So in this case, it's like fraction. I have hours on the top, hours on the bottom. Those two will cancel, and my final units is just miles. So I've got miles, I copy that over here, and then 50 times 40 is 200. So I know that if I drive 50 miles an hour for 4 hours, I'll go 200 miles, okay? Now let's change it up. If I say I'm going to drive 200 miles at 50 miles an hour, how long will it take to get there? Then I can manipulate this. What I do is I divide both sides by v, okay, and then I get x over v here, and then bt over v, I get t, so time gives me x over v, and we'll go through that. And so let's check it out. My distance is 200 miles. My velocity is 50 miles per hour. So I have 1 mile upstairs, 1 mile downstairs. Those cancel. But then what do I do with this hours? I have 1 over hours. So that means I reciprocate, I turn it upside down, and that actually comes up upstairs. Okay, so 1 over gets me back to the same thing. So my units is hours, and then 200 divided by 50, work it out in your calculator. You'll need that for the quiz on next week. That's 4 hours. Okay, so we just went around in a circle and everything's fine. Okay, so these are the kind of things we expect you to be able to do. And, we'll use the fact that, for example, the speed of sound is 350 meters per second. How long does it take to go this distance or that distance? So let's do some conversions now. And conversions, again, I always like to start with something that is obvious and I know, just to make sure I'm doing it right. And so you probably all pretty well know that 1 yard is the same as 3 feet, okay? And then I'm going to write this in a bit of a funny way. I'm going to write it like this. 3 feet is the same as 1 yard. So because this is the same as this, when I divide the two, I just get 1. It's like saying 57 over 57, that ratio is 1. So 3 feet over 1 yard is equal to 1. And so I want to know how many feet is 100 yards. And what I'm going to do is I'm going to take 100 yards and I'm going to multiply that by 1. But I'm going to multiply it by 1 in a special form. If I multiply it by 1 in this form, it'll be the same thing. And I happen to know that 3 feet is 1 yard. So the way I've got it set up here, let's look at the units. I've got yards upstairs, yards downstairs. So those will cancel, and I'm left with feet. And that copies over, and that's good because that's what I want. That's how I knew to put 3 feet over 1 yard instead of upside down. Okay, and then I multiply 100 times 3, and I get 300 feet. Okay, so you probably could do that in your head, but just by going through this, that leads us on how to do a more complicated one. And this one is as complicated as I'm going to get, but let me lead you through that. Okay, and I will not make you do this on your own, but let me just lead you through this because this is something we need quite a bit. So the speed of sound is about 350 meters per second. At room temperature, it's about 344, but I like round numbers, so I'm going to call it 350. So I want to take 350 meters per second, which is the speed of sound, and I want to convert that into miles per hour. And I'm going to do that by multiplying by 1 a bunch of times. For example, I know that 60 seconds is the same as 1 minute. So because 60 seconds is the same as 1 minute, this quantity is 1. I'm just multiplying by 1. And I know that 60 minutes equals 1 hour. I'm also multiplying by 1. And by multiplying by enough ones with funny units, what I can do is I can convert meters per second into miles per hour. And so you let the units do that. In fact, to start with, ignore the red numbers. Let's just look at the units. I've got seconds here, and I convert seconds into minutes. I convert minutes into hours, and that's what I need. And then what do I do with the meters? Well, I can convert meters into kilometers, and I have to know roughly the number of kilometers in a mile. And if you runners know, 1 mile is about 1.6 kilometers. And so if you cross out all the units, you're left with hours here and miles here, and sure enough, you get miles per hour. And if you multiply this all through, you get about 780 miles per hour. And while I have this on the screen, this is sort of a useful rule of thumb. Notice 350, if you double 350, you get 700, okay? So roughly speaking, when you want to go from meters per second to miles per hour, it's about double, okay, ballpark. It's off by about 10%. So if I take 700 and then add another 10%, that'd be 770. I'm pretty darn close, okay? So if I say, 60 miles per hour, 60 miles per hour, what's that in meters per second? It's about half, okay? So that rule of thumb is a good conversion. More accurately, it's off by about 10%. It's more like 26 meters per second, but it's a good cross check. Okay, and this will come in handy. 350 miles per hour, 350 meters per second, 780 miles per hour. I'll be flying in an airplane coming back from Europe, and they do about 600 miles an hour. If they get too close to the speed of sound, they start to become inefficient. So typical commercial flights go about 600 miles an hour. The SSTs go above that, but that doesn't exist anymore. This is as complicated, this is as complicated as I'm going to get, but I won't give this to you by yourself. But I did want to just demonstrate that because that's a useful one. So don't panic. That's not the kind of, we won't be, doing that much heavy calculation here. Let me do one more calculation, because again, we want to get into music. And this is also a key relation. It relates the velocity of a wave to the frequency of the wave and the wavelength. So velocity, frequency, wavelength. Velocity, that could be meters per second. Frequency is hertz or cycle per second. And then wavelength is meters or feet. So let's do A440. So that's 440 hertz. That's our frequency. And again, I'm going to round the velocity speed of sound to about 350 meters per second. We'll see that's temperature dependent. That changes a little bit, but let me just pick round numbers to start. And again, I take this, and if I divide both sides by F, I find out that lambda equals V over F, and this is what I have. And again, let's check with the units. My velocity is 350 meters per second, and my frequency is 440 cycles per second. Cycles isn't one of those units. That's not a real unit. So the fundamental unit is per second. You see I have meters up top. I have per second divided by per second. That cancels with that. I'm left with meters. And the answer is about 0.8 meters. Okay, that's a little bit over 2 feet. A little bit less than a yardstick, 80 centimeters. Okay, so your A440 is a little bit larger than that. That's your wavelength. Okay. Let's do a 16-foot organ pipe, okay? And 16-foot organ pipe. Now, for 16-foot organ pipe, if it's an open pipe, that only contains half the wave. So we'll go into this later, but the actual wavelength is twice that. So the actual wavelength is going to be 32 feet inside a 16-foot organ pipe. So the wavelength is 32 feet. The velocity is 350 meters per second. I'll do the conversion in a minute, but 32 feet is about 9.6 meters approximately, depends how you round off. And so here, the frequency of that organ pipe is going to be V over lambda. I have 350 meters per second divided by 9.6 meters. The meters cancel, I have per second, that is hertz, and I get about 36 hertz. Okay, and so for most organs, they have 32 uh, 60-foot organ pipes. They get down about 36 hertz. If you have a closed pipe, you can do better, and occasionally some of the larger organs will actually have a 32-foot pipe, which would drop it an octave. And now let me show you how to go through this conversion. How did I get the relationship between feet and meters? Well, the first thing is a meter is about a yard, and it's 3 feet is a yard. So roughly I divide this by 3. 30 divided by 3 is about 10, and you can see where that is. But let's do it more accurately. 1 foot is about 0.3 meters. And so I have 32 feet. I'm going to multiply that by 1, and I use my units. I have feet upstairs, feet downstairs. Those cancel. It leaves me meters. And I know 1 foot is equal to 0.3 meters. So I get about 9.6. Okay. And so I will review that on next Tuesday and read your book in chapter 1. But those are just some of the very simple things we'll go through. We won't dwell on this, but hopefully you may have seen this before, in high school. But these are some of the very, very basics. Again, we want to move through this to get to the music and the applications, the instruments. But these are just some of the things we need to be able to figure out, okay, this A440 has what wavelength, how big an organ pipe do you need for different tones and things like that. So the last thing I want to do, that prepares you for next week's quiz, which you can review this, and I'll also try to put a link to the YouTube where I have this. But the last thing I want to do is have you look at the Powers of 10 video. And this is a classic video, and I want to show you the 1977 version, which is the original. But this is a good way of getting a understanding of the basic scale of the universe. And even though we're not going to be doing an astronomical or subatomic scales, it's just good to know what the references are. So in the video, it starts out with large scale things. And before I even get to the sun and the moon, let me talk about the Earth. How big is the Earth? Okay, we already talked about Dallas to Austin is 200 miles. How about New York to San Francisco? That's about 3,000 miles. Okay, and we already know that the speed of sound is 700 some miles per hour. So if you're traveling at the speed of sound, for example, if I had a speaking tube that went from New York to San Francisco, and I shout in one end, it would take about 4 hours for that to reach San Francisco. And so it's a good thing we don't communicate with speaking tubes. We convert them into electronic signals, and they travel at the speed of light instead of the speed of sound. But that's a reference. Another one, what is the circumference of the Earth at the equator? Well, a couple ways of doing it. You can memorize it, but there are 24 hours in a day, and there are 24 time zones, and pretty close approximation. At the equator, each time zone is about 1,000 miles. So at the equator, each time zone is 1,000 miles, and there are 24 of them. So the circumference of the Earth at the equator is about 24,000 miles, pretty close. It's actually 25, but close enough. And that means that the Earth is spinning at the equator, it's spinning at about 1,000 miles an hour. So that's a few references there. But also in the video, and you might want to pull this up afterwards, but we'll see the moon. And if I say, what's the distance to the moon? Oh, some big number of miles. But I like to convert it in things to make sense to me. And it's a big number of miles with a lot of zeros, but I can't remember that. What I can remember is it takes about a second for light to go to the moon. So when the astronauts at Apollo 13 said, Houston, we have a problem, once they said that, it actually took about 1 second to get back to Houston. And when Houston said, what's the problem? It took another second for that to propagate to Apollo 13. The sun is about 8 light minutes away. So if all of a sudden the sun turned off, we wouldn't know it for 8 minutes. And Pluto is about 5.5 hours out. So when we sent our probes out to Pluto and we said, start taking pictures, when we send that signal, only about 5.5 hours later, did the probe get it and start taking pictures of Pluto. Alpha Centauri, the nearest star, is 4 light years, and our Milky Way galaxy is about 100,000 light years across. Okay, so if you send a light beam, speed of light, it would take 100,000 light years to get across. And then the limit of our visible universe is 13 billion light years. 13 light years, just because that's the age of the universe, and there could be stuff beyond that, but there has been time for that light to get to us. That's the large scale. Let me go to the small scale now. And for the small scale, there are 3 numbers I want you to remember: 5, 10, 15. 10 to the minus 5th meters is biology, 10 to the minus 10th meters is chemistry, 10 to the minus 15th meters is physics. And if you go through the video, what you'll find is 10 to the minus 5th meters, that's about the scale. You're talking about the DNA inside the cell structure. So that's the scale of biology. 10 to the minus 10th meters, you may remember from high school, that's actually called an angstrom. And that's about the size of the sodium chloride, or a characteristic chemical bond between 2 atoms. And then 10 to the minus 15th meter, we physicists actually have a unit for that. We call it a Fermi, and that's about the radius of a proton. And so a proton is about 10 to the 15th meter, and you put a nucleus together, you got about 10 Fermi across, and that's the scale of physics. And in fact, that's what I work on. I work at the Large Hadron Collider in Geneva, Switzerland at CERN, and also they're on New York and Long Island, they're constructing an electron and ion collider to collide nuclei and electrons. And so we break them apart and look at the electrons and protons and neutrons and the quarks and gluons inside that. So do take a look at the Powers of 10 video, and you might want to just pull this up for reference. There won't be a quiz on this, but just so you have a scale of the universe we're looking at, I think that's quite interesting. So I will stop here. That's all there is. And again, there will be a quiz on Tuesday at the beginning of class, and it will cover roughly these types of concepts. I'll go over these again. And so I've posted these PDFs on the Canvas, so you can take a look there. And hope you have a good afternoon. And I'll turn it over to Brandon and Professor Baker for the rest of the class. Thank you much.